Is there a... I need to plug the computer here. The USB for the pointer? I mean to pass the slides. It's okay. Well, I'm Miguel Vioque. I'm going to tell you about new UX Ori type candidates we've detected within Gaia using machine learning techniques. I'm doing my PhD at the University of Leeds. My supervisor is Oudmaijer, who was supposed to be here and give a talk, but unfortunately he couldn't make it, so he sends you regards. So I'm going to go quite fast because I think you know all this. This is an HR diagram of different premium sequence tracks of different masses. Different colors indicate different stellar interiors. And as you know, this is how we classify premium sequence objects from the lower mass T-Tauri stars, intermediate mass T-Tauri stars, and then at the high mass end we got the Herbig AEB stars. And canonically we say that they are between 2 and 10 solar masses. Now, we know a lot of things about T-Tauri stars, but we don't know that much about the higher mass stars. For example, we understand low mass star accretion, but we don't understand high mass star accretion. And this is mainly because we know thousands of T-Tauri stars, but we only know around 260 Herbig stars. And it's not only that they are few, but this is a very unhomogeneous and biased set. And you can see this if I rescale this plot, and now using the same scale, I overplot all the known Herbig stars. And thanks, Timo, for showing this before. This is a study we did with Gaia DR2 parallaxes. We convert them into distances, and then we plot all the known Herbig stars in the HR diagram. And you can already see that, for example, we got many more low mass Herbigs than high mass Herbigs. This is partially because of the initial mass function, but also because higher mass premium sequence objects, they evolve faster, so they are more likely to be found close to the main sequence, and also they become optically visible later. So basically, we are missing all the less evolved high mass premium sequence objects, which are very important for understanding high mass star formation. So we decided that it was necessary to find new Herbigs within Gaia. But before moving on to that, in this study, we realized that it was possible to study the optical photometric variability properties of this set of Herbigs. And Timo already mentioned this too, but the idea is that Gaia does not provide variability information for Herbig stars. But we can take advantage of the fact that it's an astrometric satellite and is measuring the same object hundreds of times. So the idea, was inspired by the work of Dixon et al. In different objects, is that in the final Gaia catalog, after all the measurements, sources that are variable will have a final larger error in the Gaia flags with respect to their flags than sources that are not variable. And of course, you need to scale with the square root of the number of observations, because the more you measure something, the less error you've got. So we were able to construct this variability indicator, this proxy variability, and we realized that it was very good for tracing irregular photometric variability. We did some science with it. Here I'm showing you this variability indicator, so irregular photometric variability with respect to the mass of the Herbigs, and we found that high mass Herbigs were less variable than low mass Herbigs. But we also found that above a certain threshold, we were recovering all the known uxors in the sample, which means that this variability indicator is very good at tracing uxors. Uxors that are more variable than 0.5 magnitudes in the optical. This is kind of the resolution limit of this variability indicator. And at the time, we already proposed that all these Herbigs that were also very variable but were not cataloged as uxors, we also proposed them as possible UX Ori candidates. But this is what we did in the past. But now, as I said, we were interested in finding new Herbig stars within Gaia. And I also wanted to do machine learning to be popular. So the problem is that, as I said, we only know 260 Herbig stars, and those are not enough for machine learning techniques. They are too few. So our strategy was, okay, let's aim for all kinds of premium sequence objects using an algorithm that is biased towards the high mass end. And then after the selection, we can further select the objects that are massive. And how do you find premium sequence objects? Well, these are the main observational characteristics of premium sequence objects, infrared excesses, H-alpha emission, and photometric variability. So these observables, they work great for identifying low-mass premium sequence objects. But they don't work as nicely when it comes to identifying high-mass premium sequence objects. And this is mainly because Herbig stars are very similar to some other objects, but especially to classical BE stars, which are not prime-sequence objects, as far as we know, but they also have all these characteristics. So we wanted to construct an algorithm that was able to tell the difference between these two types of objects, and we wanted to perform an homogeneous selection of new Herbig stars, and we wanted that selection to be distance and position independent. And this has to do with how machine learning works, but just because of the fact that most known prime-sequence objects are very close by and in star-forming regions, just because it's easier to find them close by and in star-forming regions. For example, if we input distance in the algorithm, it will think that being close by is an intrinsic property of prime-sequence objects, and it will be biased towards finding objects that are close. In order to do this, I constructed a rather complicated algorithm, but the base, like the core of the algorithm, is a neural network. And I'm not going to give you much details about this, but in short, this is supervised learning. This means that we need to train with a training set, which is a list of sources that we know and we control. And important things are, there are three important things we need to choose before doing the network. The first is like which objects do we want in the training set. Of course, we want the training set to be as large as possible, but also as little contaminated as possible. Which characteristics do we want to train on? Do we want to use colors, photometry, distances? And which categories do we want to categorize? Do we want to tell the difference between irregular and regular galaxies, or do we want 4 types of elliptical galaxies and 3 types of spiral galaxies? Then comes the programming part. I'm not going to give you any details about the network. As you can imagine, there are tens of hyperparameters to choose. Actually, most of the works and the time goes in here. If you are interested in how neural network work or how the algorithm was created, just come talk to me anytime this week. But for the purpose of the talk, just some magic happens here. And as an output, at the very end, we end up with a trained neural network. And for every input object, as an output, we get the probability of the object of belonging to any of the chosen categories. And we also get some kind of metric or number that tell us how well the network is doing. So now we just need to select these things for our problem. And this is kind of easy. The characteristics needs to be relevant for the problem of matter. As I said, these are the main observational characteristics of prime-sequence objects. So we just need to choose physical information that describe those characteristics. From all whites, we took the 4 white passbands and the 3 2-mass passbands. This is near and mid-infrared. From IFAS and VFAS, which are 2 H-alpha surveys, we took the Armenos H-alpha color. And from Gaia, we took the 3 Gaia passbands and 2 variability indicators that are similar to the one I mentioned before. And well, of course, and then what we did was to combine all the passbands to create all possible colors, because we need to work in color space to be distance independent, which is important. Then we need to select the categories, also easy. We want a category of prime-sequence objects, because it's the whole point of everything. We want a category of classical BE stars, because we know they are very similar. And we want a category of other things, just so the algorithm doesn't think that everything in the galaxy is either a prime-sequence object or a classical BE star. And then we need to construct the training set. Before doing that, we can ask ourselves how many objects are there with all the known characteristics that we're using. So we just cross-matches the service that we are applying, and we end up with 4,100,000 objects. And from here, we can withdraw our training set, and it's just, we are using 850 prime-sequence objects, only a small fraction are Herbigs, 800 classical BE stars, and then 500,000 other objects that we just randomly sample from here. That was all the information we needed. Now we can train our network, and after a few hours or a few days, depending on your computer, we end up with a trained network that we can basically apply to all the objects with the information that we're using or that we use for the training. And this is our result. Here I'm showing you on the vertical axis the probability for every input object of being a classical BE star according to a network. On the horizontal axis, the probability of every input object of being a prime-sequence object according to a network. And you can imagine a third perpendicular axis to the screen with the probability of being something else. And now we said, okay, if we take the objects that are more than 50% likely of being prime-sequence, and we call them prime-sequence candidates, and same with the classical BE stars, we can say that we are recovering 8,500 prime-sequence candidates, 636 classical BE candidates. And then we have like 1,300 objects that the algorithm thinks that they are either premium sequence or classical BE, but it doesn't know which one it is. Of course, this selection of 50% is totally arbitrary. You could have gone for 95% if you want to be very precise, or you can choose 30% if you want to be very complete. But 50% sounds nice. As I said, we got some metrics as a result, and we know that the completeness after evaluation on test set is that around 80%. This means that we're retrieving 80% of the premium sequence objects that are present in the combination of catalogs that we're using. And now we want to evaluate this selection. So this is our results. We want to evaluate them, and we need to use independent analysis for evaluate this. So we need to use variables or features that the algorithm hasn't used or haven't seen for the training. And as I said, the selection is totally distance independent. So this means that the H diagram is independent of the selection. Here I'm showing you 4 Gaia H diagrams. The black contours are just Gaia sources within 500 parsecs to guide your eye. And when we overplot the premium sequence objects, candidates, we find that even though the H diagram is independent of the selection, premium sequence candidates appear where premium sequence objects are supposed to be. Not only that, but if we move up in probability, so each plot represents premium sequence candidates above a certain threshold. If we move up in probability, we get rid of the candidates that are located in the less likely premium sequence positions. And similar thing we can do on the coordinates. Again, the selection is totally independent of the positions in the sky. And if we plot the objects, this is galactic coordinates, so this is galactic longitude and galactic latitude. When we plot the premium sequence candidates in the sky, we see that they appear clustered, as we will expect, and they also trace known star-forming regions. So this independence analysis tells us that we have robust evidence to believe that the algorithm somehow is understanding the nature of these premium sequence objects, and that we are actually retrieving real premium sequence objects. And now going back to the beginning of my talk, as I said, we have this variability indicator that is very good at tracing UXORs above a certain threshold, and that we already proposed 31 new candidates. Now we can see how many new candidates we have in this new catalog of premium sequence objects. And the numbers go up a bit. Here, this is the variability indicator again. The scale is different because we use a different equation, but it's the same idea. And here I'm showing you the probability of being premium sequence according to a network. And you can see that the amount of UX Ori candidates is huge, but it's not only very large, but it's also 40% of our final catalog of candidates. This means that this irregular variability is very important for identifying premium sequence objects for the network, or it's very important for telling the difference between similar objects to premium sequence objects. And you can see that when we get closer to 1, so the objects that the neural network is very sure that they are premium sequence, the amount of very variable objects goes up drastically. I think that if you want to be very conservative, you end up with 200 UX Ori candidates. And well, this is just so you don't think that everything is so nice. This is a color plot of the premium sequence candidates, R minus H alpha and R minus I. Basically, this is the main sequence, and if I go left, I'm getting redder, and if I go up, I'm getting H alpha emission. And we realized that there were a bunch of premium sequence candidates that had a crazy amount of H alpha emission, like an impossible amount of H alpha emission. And after studying them, we noticed that we were detecting planetary nebula as premium sequence candidates. And planetary nebula has nothing to do with premium sequence objects. But then we realized it makes sense and that we can blame our network because planetary nebula, they've got emission, they've got infrared excess, and they are extended, which means that they have larger Gaia errors, which means that for us, they appear as very variable. So we are classifying them as premium sequence too. This is an example of how cautious you need to be when applying machine learning techniques, because it's very easy to introduce unwanted bias or selections. And just to conclude, we're doing spectral follow-up observations, so all these premium sequence and UX Ori candidates. This is kind of the main result of the work. We know 260 objects, and after this analysis, we are proposing more than 3,000 new Herbig candidates, and in a much more homogeneous fashion. And the final numbers are we are finding 8,500 new permission candidates, of which, by the position in the H diagram, 3,000 of them seems to be Herbigs or high mass ones, with a completeness of 80%. And regarding the UX Oris, a lot of them, like 3,500 of them, might be UX Ori type candidates. And this is an example of an UX Ori candidate that we observed this summer at the INT. This is the H-alpha spectral line. As you can see, it's just what the doctor orders, how this alpha spectral line should be of a UX Ori star. And, well, I didn't mention this, but also by accident, we also created a catalog of new classical BE stars. I think that's all. Thank you.
In your training set, you use the variability as one of the parameters to train. Don't you then make a bias already that when you then, it's not surprising that most of your selected primary sequence stars have high variability, and then you get the 40% conclusion, which might be too high because of this bias?
Yes, we're introducing several biases, actually, when we demand the rates. But in the case of the variability, we are using the variability, in the training, we're using the variability of premium sequence objects according to Gaia. So it's not a bias, an artificial bias, let's say. We are tracing the variabilities that the premium sequence objects already have. For example, a bias that we're introducing is by demanding to have detections in W4, so we are demanding to have detections in mid-infrared. We're introducing a very strong bias towards objects with a lot of infrared excess. But in the case of the variability, I don't think it's that way, because some of the Herbigs are actually not very variable, like the high mass ones. I think it's more related that the premium sequence objects really stand out in this irregular variability, whereas other similar objects, like the classical BE stars, they don't. And that's why it seems to be so important, but just because it helps to disentangle, but not because it helps to identify premium sequence objects.
So I have two questions. One, so neural networks don't naturally produce probabilities, and they usually push things between 0 and 1. So I was really interested to see that in your plot it was pretty filled out. So I was wondering if you implemented some sort of like Bayesian neural network to translate those into probabilities. And then the second question is, your training set looked very unbalanced, and I was wondering if you ran into problems with that and how you solved them.
Well, regarding the first question, well, I'm showing you. It seems well distributed, but if you think that there are 4 million objects, it's actually not that well. Yeah, the dots are very big, but here there are 4 million objects, and most of them are here, so it's not homogeneously. And yes, we're thinking about, well, I'm thinking about publishing this, but we are thinking about improving this algorithm for further selecting other objects and refining this using more advanced or different techniques. And regarding the, oh yes, and this is actually a very good question. Regarding the unbalanced, I don't know where I have it. Regarding the imbalance here, yes, there was a big thing to deal. We used some techniques. The principle of them was to basically rebalance the weights for the network. So for the network, a premium sequence object is like 500 more important than other type object. That was the main thing, but we used different techniques to deal with the fact that we have a very skewed problem. And that's also introducing some biases in the final selection that we need to discuss.
So about your training set, so it comes from previous observations of known premium sequence stars, right? So the training set is a data set from previous observations, right? So is it possible to create a grid of models and then give these model results as a training set? Do you think that's a good idea?
You mean use models instead of real stars?
No. No, I mean, you make theoretical models to predict a star will have this kind of SE.
And then you use it for training.
Yeah.
Yes, so creating fake data for training, that was another option. So this training set is extremely small. This is ridiculous, like for a machine learning project. I managed it to work, but it's very small. So one idea is just to create fake stars, but then you really need to believe your models, because any small bias in your model will propagate throughout the selection. So we decided that we don't understand Herbig's enough for doing that. But yes, that's an option. That was galaxy people do mostly, just to create fake galaxies and then.
Yes, please. Many years ago, when observers selected UX Ori type stars, they use not only amplitude of variability, but also histogram of activity. If you have for each object some statistic, for example, 70 observations, you can obtain the histogram of activity. And this is also very important criterion. Maybe this is not UX Ori, but maybe also only variable star. But histogram of activity can show you more exactly that this UX Ori or not.
Yes, I'm waiting for Gaia DR5, or when are you going to publish the whole? 4, okay. So maybe for my third postdoc, I can do that. But yes, this is...
Last question. Can you tell more details on the neural networks that you use? What's the number of layers of hidden layers and the activation function and the size of hidden layers?
Yes, I can. I have it in the backup slide, actually. Yep. So this is kind of the technical part. So this is a bit of the technique we use, especially for this skew training set, and this is kind of the summary of the architecture that we're using. So we're using a very narrow network, but very, very wide, extremely wide, and this was one of the big surprises of the project. But then we are applying a lot of regularization. So basically we're using a huge network for a small problem, but it's a very stupid network. It's very stopped, very regularized. And the test sets, we keep it very small because we don't have that many Herbigs, and we need them for the training.
And the activation function?
The activation function, I don't have it on the top of my head, but I can tell you now because I have the code here, so we can check.